We're going to find the radius and interval of convergence for this series here. We're going to apply the ratio test. So let's begin by taking the limit as n approaches infinity of n plus 1 factorial times 2x minus 1 to the n plus 1 over n factorial times 2x minus 1 to the n. When you simplify this, you get the limit as n approaches infinity of n plus 1 times 2x minus 1. And the reason why you get that is because your n plus 1 factorial is n plus 1 times n factorial. And then the 2n plus 1 to the nth power will simplify with the factor in the denominator. Again, you're taking the limit with respect to n. So 2x minus 1 is considered a constant. So we have the limit as n approaches infinity of n plus 1. Well, the limit as n approaches infinity of n plus 1 is approaching infinity. So it doesn't matter what your x is, that limit will always go towards infinity. So because that limit will always go to infinity, we can say that this series will only converge at the center. So the radius of convergence is 0. Now, what is the center? The center, remember, you need to have your power series in the form of sigma as n goes from 1 to infinity of c sub n x minus a to the nth power. So we are going to need an x minus a. Well, we have 2x minus 1 to the nth power, so somehow we need to make it look like x minus a. I'm going to factor out a 2, and we're going to be left with x minus 1/2. So this becomes 2 to the n times x minus 1/2 to the nth. So if we rewrite that power series, we have sigma as n goes from 1 to infinity of n factorial, 2 to the n, x minus 1/2 to the n power. So we can say here that a is equal to 1/2. So bringing it back to the center, the radius of convergence, and the interval of convergence. So we are going to have the power series centered at 1/2, and the power series will only converge at 1/2. Okay, so we have the centered at 1/2, and the series will only converge at 1/2. So that means that the radius of convergence is 0. And the interval of convergence will be from 1/2 to 1/2, which we really write as 1/2. All right, I will stop right here.